Hey Ramblers, this video covers chapter 9.4 in our textbook, and it's titled Geometry's Most Elegant Theorem, the Pythagorean Theorem. Now the Pythagorean Theorem has been around for thousands of years, certainly thousands of years before Pythagoras discovered it. I'm not sure Pythagoras ever really did discover it, but he certainly has his name stuck to it. This relationship between the sides of a right triangle and its hypotenuse, that the sum of the squares of the sides equaled the square of the hypotenuse, was a relationship that the Egyptians were aware of when they built the pyramids thousands of years before Pythagoras, and the Persians in the Middle East were also aware of this relationship, as were the Chinese. So to think that Pythagoras really is responsible for it may not be exactly accurate. Nevertheless, it is probably one of the most useful theorems in all of mathematics, and certainly one which I think you'll learn to appreciate the elegance of and the utility of. So we'll prove that first in this video, but then we're also going to look at the converse of the Pythagorean theorem. And this is very important as well. Maybe not quite as useful, but certainly a truth that you're going to want to be familiar with. So not only is the Pythagorean theorem that a squared plus b squared equals c squared true, but also you'll learn that if that relationship holds true, that a squared plus b squared equals c squared, then therefore the triangle must be a right triangle. That's the converse. So please watch the video, take good notes, and I hope this helps you to understand the material. Thanks for watching. The Pythagorean theorem is probably the most famous theorem in all of mathematics, and it really is simply stated as a squared plus b squared equals c squared. There's a little bit more to it than that. Really, the theorem should state, given a right triangle, the sum of the squares of the legs equals the square of the hypotenuse. And that given that we're talking about a right triangle is often overlooked, especially early on in chapter 9, as students are just getting used to using this theorem. So you have to be working with a right triangle. And if so, the square of the legs, which we're calling A and B, added together will equal the square of the hypotenuse, which is of course the side opposite the longest angle and opposite the right angle and is the longest side. So let's go back to a familiar diagram from our work in the previous video, which we're going to use in the proof. So I'm referring to A as leg A, B will be leg B, and what the theorem calls c squared, of course, we refer to as the hypotenuse. All right, let's take a look at this proof. And I think it's rather interesting how simple it is, given the power of this theorem. All right, ABC is a right angle is our only, ABC is a right triangle is our only given. And then we, of course, draw CD. That is the altitude drawn from the right angle to the hypotenuse. Well, we know from our previous video that leg A squared equals part A times the hypotenuse, and leg B squared equals part B times the hypotenuse. So if we add leg A squared plus leg B squared, we get part A times hypotenuse plus part B times hypotenuse. Well, factoring out hypotenuse from each of these terms, I'm left with leg A squared plus leg B squared equals hypotenuse times part A plus part B. Now, take a look at our diagram again. Part A plus part B is equal to the hypotenuse. So I can rewrite part A plus part B as the hypotenuse, which means leg A squared plus leg B squared equals hypotenuse squared. Substituting back into the more familiar version of this theorem, we get a squared plus b squared equals c squared. And that's the end of the proof. So really, it's incredibly powerful, but you have to make sure you're working with a right triangle. And if so, then leg A squared plus leg B squared equals the hypotenuse squared. So let's add this to our list of formulas for this chapter. And now let's take a minute and prove the converse of the Pythagorean theorem. Okay, now let's talk about the converse of the Pythagorean theorem. The converse, as you recall, is when we switch the givens and the conclusion. So here we're going to say if the sum of the squares of the two smaller sides of a triangle is equal to the square of the largest side, then the triangle is a right triangle. So in other words, if a squared plus b squared does equal c squared, then the triangle is a right triangle. You'll recognize that as the converse of the Pythagorean theorem that we just talked about. Okay, so what does that mean? Well, let's take a look at this diagram. So long as a squared plus b squared is the same measure as c squared, then I can be sure that this is a right triangle. And sure enough, as I move that about, the angle stays 90 degrees. That angle at C is right here. Now, oopsie, I can keep moving that around. And so long as I keep the sum of the squares equal to the square of the hypotenuse, it's a right triangle. But what happens when I do something like that? Now the sum of the squares is greater than the square of the hypotenuse. And you'll notice that I no longer have a right angle, that my angle is 53 degrees. Well, that's an important consequence of the converse called a lemma. A lemma is a conclusion that directly follows. And the lemma says this, that if a squared plus b squared is not congruent to c squared, then the triangle is not a right triangle. And if a squared plus b squared is greater than c squared, as it is in our example here, then the triangle is acute. If I were to change this angle, or I should say if I was to change and make c squared greater than a squared plus b squared, then we can know that the triangle is obtuse, even though I spelled it obtuse. Sorry about that. So, that's really important that you get this theorem down, that if a squared plus b squared is equal to c squared, like they are right now, then we have a right angle. But if they're not equal, and a squared plus b squared is greater, we have an acute triangle. If they're not congruent and c squared is greater, then we have an obtuse triangle. Okay, that's the converse and its immediate lemma. I hope this stuff helps. Good luck on the exercises for this chapter.